Okay, good morning, everybody. So welcome to the second RIKEN AIP and Shanghai Jiao University Computer Science Joint Workshop on Machine Learning and Brain-like Intelligence. So I'm Masashi Sugiyama. I'm Director of RIKEN Center for AIP. So let me briefly give some opening remark and then introduce RIKEN AIP briefly. So first of all, so we had the first round already 5 years ago. So it's quite a long time ago. So in 2019 March, we had the first workshop in Shanghai. That was really fantastic. That was before COVID, so it was quite a long time ago. But we had quite nice memory of that. Then, so during the workshop, we signed the MOU, Memorandum of Understanding, between two organizations. So we are nice partners still. But unfortunately, so our activities were not so active during the COVID-19 because we couldn't really communicate easily. So now it's time to restart our new MOU, and so hopefully this workshop is a kind of kickoff of the second round of our MOU. Then this is the program. So thanks Qibin for organizing such a nice program. We have a lot of great talks, and also we have poster sessions during the coffee break in the afternoon, so today and tomorrow. So we have a lot of nice talks and nice posters. So let's have nice discussion over those presentations. Okay, that was the brief introduction of the workshop. So let's enjoy the workshop. Then, so my next part is about the introduction of RIKEN Center for Advanced Intelligence project. So RIKEN actually has a relatively long history, started in 1917 as a private foundation. So it's actually private. It was a private. Then, so one of the founders was called Eiichi Shibusawa. He is actually now a famous person because we have a new 10,000 yen bill, and he is printed on this bill. Then, so RIKEN became a quite big group, big entity, and it was called RIKEN Concern. So in 1939, so RIKEN had 63 companies and 121 plants. So it was really a big entity. So it was quite successful, but because it was quite successful, it was regarded as a kind of dangerous entity. And after World War II, RIKEN was so broken up by the United States, unfortunately. But in 1948, RIKEN restarted as Scientific Research Institute Limited. And then it became a public corporation in 1958. And now we are National Research and Development Institute. So we are fully public institute now. And entire RIKEN is actually quite big. We have 2,900 researchers and 500 admin staff. So it's a huge entity. And roughly, we have 15 centers and projects. And they are very roughly, so 6 are physics-related research centers, and 6 are life science-related centers, and 3 are informatics-related centers. So one is on robotics and supercomputer, and our Center for Advanced Intelligence project. Then, so our AIP, so RIKEN founded the Center for Advanced Intelligence project in 2016 under the Ministry of Education, Culture, Sports, Science, and Technology. And we have about 130 employed researchers, and 40% are international researchers, and 1/4 are roughly female researchers. So we are quite diverse. Then we have about 250 visiting researchers from domestic universities and international universities, and also some companies. Then we have 130 domestic students as part-time researchers, and also we have more than 140 international interns in total. Then we have many international collaboration partners, including Shanghai Jiao University, and also we have many industry projects. And our main center is located here in Nihonbashi, so we are located here. But many teams are also distributed in different universities in Japan, like from Sendai to Tsukuba, and so Shiga, Kyoto, Fukuoka, and things like that. Then in RIKEN AIP, we have 3 research groups. The first group is called Generic Technology Research Group. And here we have 13 teams working on like machine learning and inference algorithms, like robust estimation, Bayesian inference, and high-dimensional statistics. Or some even theory people working on statistical and optimization theory. So they analyze the convergence of algorithms, non-convex optimization, and things like that. The second group is called Goal-Oriented Technology Research Group. And here we have 17 teams. And roughly they are divided into two subgroups. And one aims for AI for science. So they try to use state-of-the-art AI technology for advancing sciences, like cancer research, material science research, and genomics research. And the other half is working on AI for societal problems. We are a national institute, so we try to contribute to the public. Like projects are including natural disasters, elderly healthcare, education, and things like that. Then finally, the third group is AI in Society Research Group. And here we have 6 teams, and they are working on more societal side of AI and machine learning, like personal data management, AI security, economy and management, and ethics and governance, things like that. So all 3 groups are quite different and quite diverse, but we are all together in the same center, and we are communicating with each other to explore new topics in this field. And so this is just a brief sketch of our research results. And in developing new AI technologies, so people working on theory of deep learning and also developing new methods of machine learning. Then for accelerating scientific research, so they are working on medical science, material science, and also data-driven science methodology. Then, so to solve socially critical problems, so they are working on natural disasters, elderly healthcare, and education, and things like that. Then finally, so we are studying AI ethical, legal, and social issues, like setting up AI ethical guidelines, or so we work on personal data management. And also more recently, we are interested in AI security and reliability. So these are kind of urgent challenges internationally. So okay, so these are a rough sketch of our research. And hopefully, so actually we have many researchers in RIKEN AIP, and subset of them are attending this workshop. And through the 2-day workshop, hopefully we can have more discussion and find new common challenges together. Thank you very much.
So the first talk will give by Professor Masashi Sugiyama, and he will talk about the recent advance in robust machine learning. Yeah, please.
Okay, so thank you very much. So this time I speak as a team leader of imperfect information learning team at RIKEN AIP. So my talk is about recent advances in robust machine learning. And for RIKEN people, so our progress is quite slow. So maybe most of the contents are quite the same as what you have heard previously. But for Shanghai Jiao University people, hopefully I can convey our recent advances about robust machine learning. Okay, so our team, so we are developing novel machine learning algorithms that allow reliable learning from limited information. So nowadays, so machine learning algorithm requires a huge amount of data, but often such data is kind of limited in information. For example, like supervision included in the data is not sufficient, and I call it weak supervision. But hopefully only from weak data, we can still guarantee that our algorithm produces a kind of reliable solution. So that's one challenge for us. Then the second issue is label noise. So once we have more data, so then data is more noisy. In particular, labels are often given by human experts. And human experts are so busy, so then they make a lot of mistakes if we have huge number of data. Or if labels are given semi-automatically by some sensors, then so they are also quite noise prone. Then finally, data bias. So this is also a big issue nowadays. So classically, we worked on this data bias issue as a kind of changing environment over time, because the world is changing over time. And hopefully our machine learning system can overcome this changing distribution, changing environments. That was the starting point. But nowadays, bias is more serious in terms of the privacy issues. Because given some test environment, we are not allowed to collect data as we wish because of some privacy concerns. So then our data is kind of biased compared to the test environment. But still, hopefully, we have a kind of unbiased solution to the test environment. But this is the third challenge here. And we are tackling these issues in our team. And we have nice members in our team. And also, Min-kun was just joining in this August, so last week. So we have new members. And in addition, we have many great visiting scientists from different countries and also part-timers and interns. They are really doing great jobs. So we have like a big team, including these visiting scientists, part-timers, and interns. Okay, great. So then let me start from the first topic of weakly supervised learning. So all of us know that supervised classification from big label data is quite successful in many application domains, like speech recognition, image understanding, language translation, so advertisement, etc. So these are typical classification problems in binary setting and multi-class settings. But in many other application domains, like in our RIKEN Center, we are working on some medical projects, or natural disasters, robot control, brain signal analysis. So in these applications, so collecting big label data is actually not straightforward. So sometimes they are very costly, or sometimes even it is impossible. Like we have a lot of natural disasters, like a lot of earthquakes in Japan, but still it's not big data. It's quite less frequent. So to cope with this problem, I want to say, okay, we want to do machine learning from small data. That's a kind of ultimate goal. But learning from small data is not really statistically possible. So then our idea is, so we still need large number of data points, but they are not fully supervised, but only weakly supervised. So that's the situation. And what do I mean by weak supervision? So one typical example is called PU classification, positive unlabeled classification. So in the case of binary classification, we typically need positively labeled data, negatively labeled data, and train a classifier. So that's a standard situation. And if the number of data points is n, then the classification error decreases in the order of 1 over square root of n. So this is a standard analysis. But now, so we only have weak supervision. For example, in this PU classification case, we only have blue points, so positive points, and unlabeled data, black points. And we don't observe any single negative data. So that's a typical PU classification problem. We only have positive and unlabeled data, but still we want to classify positive and negative. Okay, we have a lot of applications of this PU classification, and we had nice theory and algorithm in the last 10 years or so. And here's one slide summary of the methodology here. So we basically try to estimate the classification risk only from PU data. So that's the technical challenge here. And I don't really go into the detail today, but our classification risk can be decomposed into the risk for the positive data and risk for the negative data. And in the standard supervised learning case, we have both positive data and negative data. Then these two terms can be naively estimated from data. So this is how standard supervised learning is performed. And so one notation here, pi and 1 minus pi. So these are actually class priors. And actually estimation of this class prior is quite a key challenge in PU classification. But today I just skip it because already we have some literature on estimation of class prior from PU data. And we just assume pi is known today. Then the rest of this part. So in PU classification, so we have positive data. So the first term can be still estimated from data naively. But the second term is completely unknown because we don't have any single negative data. So how do we handle this term, R minus? And here's a very simple solution. We use this relation. So unlabeled data density, P of x, is naturally a mixture of positive data density and negative data density. And the mixing coefficients are pi and 1 minus pi. Like we have positive data density and negative data density like this. Then unlabeled data density is a mixture of these two, like black dotted line. And these are just equal. And we use this relation to eliminate the expectation over negative data points. Then we end up in having these two terms. Then now everything is expressed in terms of positive data and unlabeled data. Then we have a unbiased risk estimator in a naive way. So that's the kind of basic solution to this PU classification problem. So we want to minimize the classification risk, but we don't have positive and negative data, but only positive and unlabeled data. But still, we could show that only from PU data, we can estimate it unbiasedly. So that's the solution. And to make it work, we need a few more tricks to improve the performance. But this is actually a basic solution we had already 10 years ago. Then here's a nice application of PU classification. So it's signal enhancement or noise removal. So we have noisy speech here. And we want to eliminate noise and we want to have a clean speech. So that's the task here. It's straightforward. And to achieve this kind of goal, so typically we use so-called parallel training data. So parallel means for the same signal, we want to have a clean version and noisy version. So once we have like a clean version and noisy version of the same data, then we can actually train a signal enhancer or noise remover based on these parallel training data. But in practice, such parallel training data is not really available because it's impossible to have clean and noisy version at the same time. Then typically they generate synthetic noise and add this synthetic noise to clean signal recorded in some studio. But this doesn't generate so well in reality because the noise part is synthetic, artificial. Then our case, we just use PU classification. And in this setting, the positive class is actually noise. We put a microphone in a noisy environment and just collect noise. So these are actually positively labeled data in our context. Then in the same environment, we ask a subject to speak. So this is actually unlabeled data. So it's a bit tricky, but it's a mixture of noise and speech. So this is unlabeled data. Then now we have positive data and unlabeled data and apply PU classification. Then actually we can separate noise and speech, even without having clean speech. So that's a bit tricky formulation, but it's a kind of very clear formulation from the PU classification viewpoint. And in reality, so we could achieve quite nice performance. So in the SNR, so compared with the baseline method using non-parallel data, so our method achieves much higher signal to noise ratio. And our method is closer to the supervised counterpart. Of course, this is the best, but our method is achieving closer number to this supervised counterpart. So this is the kind of usefulness of PU classification. So one class can be collected quite easily. Like in this case, pure noise can be easily collected. This is the only label information we need, weak supervision. Then unlabeled data is just kind of randomly collected in some environment. So this is for free. But still, we can perform supervised learning in this context. So that's quite good. That was one nice example of weakly supervised learning. But the same methodology can be extended to many different similar problems, like learning from positive confidence information. So in PU classification, we required blue points and black points. But now we only have blue points, only positive data. So in some privacy concern situation, so this often happens. But as long as we have positive points with confidence, it's actually class posterior probability. So this point belongs to the positive class with 70% or 20%, 5% or something like that. Then only from positive confidence data, again, we can train a classifier with guarantee. And more challenging scenario is called UU classification. Now we don't have any single labels, but instead we are given two sets of unlabeled data. But two sets of unlabeled data have different class priors. Like in one data set, we have 70% positive, 30% negatives. And in second data set, we have 20% positives and 80% negatives or something like that. Then only from two sets of unlabeled data having different class priors, we can still train a classifier in a supervised learning way with guarantee. Like rough intuition is that, so okay, we have two hospitals and they have a large number of unlabeled medical images. And medical doctors are so busy, so those medical images are unlabeled. But still, we have a prior knowledge that in one hospital, 20% of cancer patients exist, and in second hospital, 40% are cancer patients or something like that. Then only from two sets of unlabeled medical images and class priors, we can train a classifier, and we can identify whether cancer exists or not in images. in principle. Maybe it's a mathematical method. It doesn't work so well in practice. But mathematically, we can solve a problem in that way. And as a special case of this UU classification, so similar, dissimilar, paired data can also be used for training a classifier. So this is quite useful for some sensitive prediction problems. And we have a lot more variations in multi-class problems. So if you have classes more than 2, so then labeling is actually more costly. Suppose we have thousands of classes, then labeling takes a lot of time. So weakly supervised learning for multi-class problems is actually even more important. And we have nice similar theories for different types of weak labels. And finally, so we summarized all of them and published a book 2 years ago. So machine learning from weak supervision. Actually, all the methods are developed in the same framework. So empirical risk minimization, it's quite a standard supervised learning formulation. So then we can actually use any loss function, any classifier, any optimizer, and we can also use any regularization technique to improve the solution. So this is a quite general framework, but we can accommodate many different types of weakly supervised classification problems here. So that's one result we had on weakly supervised learning. Then the second part is noise robust learning. Again, the problem is quite simple. So we consider supervised learning with noisy output. So input X and output Y, and output Y is noisy now. So in the case of one-dimensional regression, so the illustration is something like this. We have one-dimensional input on the horizontal axis and output Y here. And output Y is noisy now. So not Y, but Y bar is given like this. And we want to learn a function. Then typically, so we just don't care. So we just fit our predictor to noisy output, perform linear least squares or something like that. That's a standard practice. Then in the classification case, so labels are flipped. So we should have blue points on the top left corner, but some labels are flipped. Again, these are Y bar, not Y. But typically, we don't care. We just fit our classifier to noisy labels and just minimize noisy empirical risk and hope that everything is fine. But this supervised learning from noisy output. So this is a classic problem, and maybe this has been already studied a lot. And for regression, yes. So as long as noise is independent and additive, just we don't have to care output noise. As long as we have large number of noisy output, so our solution is still statistically consistent. If you have many noisy points, they are automatically canceled each other, and it works well. But surprisingly, for classification, still we need some special care. Even if we have infinitely many label noisy label points, still our solution is not consistent. Even if we have infinitely many points, our solution is not correct. So we need a specific noise reduction mechanism to achieve statistical consistency. So it's a classic problem, but it's not solved yet. Then one typical approach is to learn with noise transition matrix. So let's call it T. And in the 3-class case, so T is a 3x3 matrix, and it represents the probability of flipping label I to label class I to class J. So that's why it's 3x3 matrix like this. Then already there's a nice theory. So 2 approaches actually. So one is to adjust classifier by T transpose to simulate noise. So this means that if we apply T transpose to our classifier's output, then noise can be simulated. Then, so this noisy classifier is fitted to noisy labels. Then the consistency can be recovered. Then another approach is opposite. So use T inverse to eliminate noise. So T is a noise matrix. Then T inverse is a kind of denoising matrix. And we apply a vectorized loss function to T inverse. Then we can actually get rid of the influence of noise, and we have an unbiased fixed estimator. So these are quite nice systematic approaches, but T is unknown in practice. So we need to estimate T from noisy data, noisy training data. And this is actually quite challenging. And we spent many years to think about a reasonable solution. And finally, we had one good solution, so estimating T under weaker conditions. So let me spend 1 or 2 minutes to briefly explain the idea in one slide. So to visualize the problem, so let's consider 3-class problem. Then so T is a 3x3 matrix. And we consider triangle. So like 1, 0, 0 here, 0, 1, 0 here, and 0, 0, 1 here. Then so the noise transition matrix T is always expressed as an inner triangle. If there's no noise, so T is the identity matrix. Then it's the same as this big triangle. But typically they are included in like this: the first column, second column, third column. Then, so interestingly, all noisy training data can be mapped in the simplex. So if you have xi and yi bar, then they are actually located inside this inner triangle always, as long as we have a reasonable noisy data following the generation process. Then our solution is quite simple. So we minimize these two terms. And in the first term, we try to obtain a triangle that contains all training data inside, all noisy training data inside. This corresponds to loss minimization. Then the second term is to shrink the volume of this triangle. So we want to find the kind of smallest triangle that contains all training data. So that's the proposed algorithm called volume minimization. And we have two justifications for this problem, for this method. The first one, suppose we have noiseless labels in our training data. Then those noiseless labels correspond to the vertices of the triangle. So class 1, class 2, class 3. Then, now we contain all points, including the 3 black points, and shrink the volume. Then, of course, we can recover the true one. So that's one justification that our method produced the right solution. Then the second case, now we don't have noiseless labels, so we don't have points on vertices. But still, we have, in this example, I put 2 points on each edge. Then in this case, if we shrink the volume and include all points, still we can recover the true triangle, right, geographically. And we have more serious theoretical mathematical condition that is named sufficiently scattered training data. As long as our noisy points are kind of reasonably noisy, scattered, then and cover the triangle entirely, then so we can guarantee that true T is always identified. But this is another justification of our method. But even without this sufficiently scattered condition, as long as training points are reasonably scattered, then we should be able to find a reasonable solution by this geometric intuition. So that's why this method works quite well in practice. Okay, that was a kind of nice, happy end of the first story. But in reality, so our label noise is even more challenging. What we have considered so far was so-called input-independent noise, or class conditional noise. So this means that noise property does not depend on input X. So we have similar noise over the entire input domain. And this is not actually natural. In practice, maybe we have more noise near the decision boundaries like this. And these points, far away from the boundaries, they are easy to classify. So maybe there's no noise. But this is the situation in practice. So this is input-dependent noise. So noise property depends on the location X. That's quite challenging. And now the noise transition matrix is a function of X. So noise transition matrix function. And even if it's a constant matrix, estimation of T was quite difficult and challenging. But now it's a function of X. So maybe there's no way we can really estimate it properly. So in the end, so we end up in developing some heuristic algorithms, assuming some additional conditions. Like true T can be decomposed into some parts. We assume we have some additional confidence scores as auxiliary information. Well, we assume that T of X is smoothed over some manifold or something like that. So these methods are good in some cases, but we can't really guarantee that they are always good because it includes some heuristics. So this is still actually an open problem. And in the end, so we decided to take completely another different approach to tackle this problem. So I just stop here, and this is still an open challenge. And I will come back to this point at the end of this talk. Then the third one is about transfer learning. So now, so training and test data often follow different distributions in many problems. Maybe due to changing environments over time, or maybe due to some sample selection bias, so because of privacy concerns. So we have two different distributions. And the target of transfer learning is to train a test domain predictor using training data from different domains. So we want to somehow transfer knowledge from training data to the test domain. So that's the challenge here. And obviously, this is not a new problem. And actually, I co-organized a workshop in NIPS 2006, so already close to 20 years ago. And at that moment, there was no proper name for this problem. And we had our workshop was named NIPS Workshop on Learning when Test and Training Inputs have different distribution. So this really explains the problem. And actually, it was a really successful workshop, and we had a lot of great speakers and discussions. Then after 3 years, actually, we published a book from the MIT Press. And there, so we named the problem dataset shift in machine learning. So, but unfortunately, this word dataset shift did not become quite popular. Then recently, this was rebranded as distribution shift. And at least in the last 3 years at New RIPS, there were workshops on distribution shift. And this is becoming a big topic again. And our old book is cited a lot these days. So it's quite nice. A book published 15 years ago, it's cited again nowadays. Then here's the basics of transfer learning. So it's called importance weighted training. So to illustrate the problem, let's focus on a specific setting called covariate shift. So covariate is the name of an input variable x in statistics. So covariate shift means input x, distribution of input x changes, or only changes. So P of x changes between training and testing, but another one, P of y given x, the output distribution does not change. Like this can be nicely illustrated in one-dimensional regression again. So horizontal x axis is the input x and output y is the vertical axis. And we have the unchanged target function here. Then training data is mostly coming from the left-hand side. And the test data is coming from the right-hand side. So because P of x is different. Then now we have blue training points. And suppose we fit these blue points by like linear least squares. Then we end up in having this green line. This fits blue points quite well, but it doesn't predict black crosses quite well. So this shows that ordinary training is not consistent, statistically consistent under covariate shift. Then what should we do? So we use importance weighted training. So now loss function is weighted by the importance. So this is the ratio of PTEX over PTR of x. Then interestingly, only from blue points and importance values, so we obtain this green line. And this predicts black crosses quite well. So the trick is that, so for blue points, for most of the blue points, the importance values are almost zero on the left-hand side. So they are almost ignored. And only a few points on the right-hand side, they are close to the test region. So they have large importance value. So then automatically, like important points are selected, and then only from small number of important points, so the predictor is trained and obtain this green line. And statistically, this is consistent. So if we have infinitely many points, we obtain the optimal solution. But estimation of importance was another challenge, and we also spent a lot of years, many years, to estimate the importance value from data. And I don't really go into the detail, but we had a book on that. Then typically, so we first estimate the importance weight. So one of the methods is called least squares importance fitting. And it's actually quite simple. And we obtain an importance estimator, R-hat. Then use this R-hat, we perform importance weighted training. So this is the kind of approach used in classical literature. And also we had a lot of industry application based on this two-step approach more than 10 years ago. But this two-step approach is actually not optimal. So we wanted to actually combine the two steps into a single step, because small estimation error in R-hat can be magnified in the second step, because two steps are solved independently. So once we can like merge these two steps and solve them at the same time, then the solution must be much better. And after 10 years, so we finally found a method to optimize R and F at the same time. So I don't really go into the detail, but we obtain an upper bound of the test risk, and it is J. And this J is actually the sum of these two terms exactly. So this is quite interesting. And we propose to minimize this J with respect to both R and F. So this means that the classical two-step approaches are clearly suboptimal because it tries to estimate, minimize J1 first, then after that J2. But now we minimize J1 plus J2 at the same time. Then we can always achieve a smaller and upper bound. And it works much better in practice. Then more recently, so we are interested in so-called sequential shifts. So far we considered only training and test. But now test is also changing over time. And we want to do a kind of online learning over time to overcome this changing distribution. And in the last 2 years, we had papers on sequential label shift and sequential covariate shift. So P of Y changes over time, or P of X changes over time. And in both papers, we use basically online gradient descent. So we obtain some unlabeled data from the test domain and estimate the classification risk, and then perform online gradient descent. And we proved that our method actually achieved the same dynamic regret as the case with known intensity without knowing the shift intensity. So we don't really assume any knowledge on the changing distribution. But as if we know the distribution shift, we can perform online gradient descent optimally. So that's the methods we proposed in the last 2 years or so. Okay, then last part. So we were interested in distribution shift, and we developed many methods. But in most of the works, we assume that we know the shift type, like covariate shift. So only P of X changes, and P of Y given X does not change, or something like that. This is the kind of knowledge we require. But actually, in practice, so knowing the shift type is the most difficult part, or impossible. So in our case, we only use labeled training data and unlabeled test data. Then actually, it is not possible to identify the shift type. So it's more like a belief. Then another problem is label noise, as I discussed already. So label noise is actually a type of distribution shift. So it can be regarded as changing P of Y given X. So in the training phase, we have noisy labels, so P of Y bar given X. But in the test phase, we assume we have clean label, and we want to estimate. Then, so P of Y given X is actually different between training and testing. So it is also a type of distribution shift. And we have noise transition here. And as I have shown already, we have a nice theory for input independent noise. So no X here. Then we have the noise transition matrix, and we had a nice method to estimate it. And we have a consistent procedure. But for input dependent noise, so X exists here, so it is still a challenging problem. Then to overcome these difficulties, our new approach is based on this joint shift. Now P of X and Y, joint distribution changes arbitrarily. So this basically contains everything. But once we have a reasonable method for this setting, then this is actually a very strong method in practice. And already we had one method at NeurIPS 2020. But in this method, we assume that we have a small number of labeled test data. So this is we require. But then based on these two sets of labeled data, so we basically train a neural network in a dynamic way based on minibatch in a standard way. And importance weight is also estimated for each minibatch. And we use a method called kernel mean matching. I don't really go into the detail here, but we have a very crude estimation of importance weight at for each minibatch. And we could somehow estimate the gradient direction, reasonable gradient direction. So maybe this method is not so accurate because we only have a small number of label test data. But as long as we can find a reasonable direction to go for each minibatch, then actually it's fine. In practice, it seems to be working quite well. So this is one of the first methods that can systematically handle joint distribution shift. Then, so this is the last slide. So more recently, so we tried to overcome the limitation of the current approach. So first of all, importance weighting requires test domain to be included in the training domain, like this situation. So PTR is actually larger, has wider support. PTE is more confined. Otherwise, the importance value tends to be infinity, and it doesn't work well. No guarantee. But in practice, so we expect to solve this kind of problem, right? So PTR here and PTE is here, and this is sticked out from the training domain. So how can we handle this out of training domain problem? That was the paper we had last year. And I don't really go into the detail, but we had the method we used the outlier detection method to identify this point and split the test points into the training side and test side, then compute the loss values separately. Then we can recover consistency, even for this out of training domain situation. Then our current challenge is to overcome the assumption that we need label test data, because this is too strong in practice. Like in the noisy label case, having label test data means we have clean labels. So we are going back to the starting point, and this is not interesting. So we want to overcome this situation. But if we assume only unlabeled test data, then there's no way we can cope with joint distribution shift. We need some supervision. Then, so I believe so a good compromise would be to use weak supervision, weakly supervised learning that I introduced in the beginning of this talk. We don't really require fully labeled data, but only weakly supervised data in some sense. Then hopefully only from weakly supervised data, still we can do the same thing. We can overcome joint distribution shift. Once we have a method like that, then that would be a really excellent method in practice. Then hopefully we can also extend that method to sequential joint shift. Then this can be a nice alternative to continual learning nowadays. People are quite much interested. So in most of the cases, continual learning nowadays is focusing on some specific aspects like new class problem or catastrophic forgetting and things like that. But once we have a systematic formulation like this and we really analyze the dynamic regret in this context, then that would be a very strong continual learning method. Then, so hopefully we can generalize this idea and hope to have machine learning with least assumptions. So that's our ultimate challenge nowadays. Because so far, most of the machine learning algorithms are developed in a way that we require some strong assumption. Then based on this strong assumption, we make a strong method and achieve a good performance. And in many applications, so research is done in this way and achieved excellent performance. So this is great. But on the other hand, in many new application projects, usually at the starting point, we don't have a lot of data and we don't have a lot of knowledge, and we only have small number of researchers to work with. Then the first step we need to do is to know whether machine learning is really useful in that project or not. From that viewpoint, so the latest state-of-the-art methods are not that much useful because they require strong assumptions behind. But once we have a machine learning method with least assumptions and maybe least guarantee, then that should be quite useful. We only have limited amount of data and almost no knowledge, but the method is guaranteed to produce some solution. Maybe the accuracy is not good enough, but it is guaranteed. Then at least we can judge whether machine learning is useful in this project or not. Then once we find, okay, machine learning is useful for this project, then, okay, now it's time to meet our boss and ask more funding and assign more people. Then we can collect more data and we can have more people in the project. Then, so we have more knowledge on the problem. Then maybe we should be able to use one of the state-of-the-art methods and then achieve better performance. So that's the kind of right steps, I think. So then what we are missing is the first method, so machine learning with least assumption. So that's something we want to develop. But still, this is an ongoing challenge, and hopefully I can obtain some hint from the discussion through this workshop. Okay, thank you very much.
Thanks for a great talk. So any questions or comments?
Okay, very interesting talk. Give a very broad view on semi-supervised learning from PEO and noise and transfer point. And the last point is reliable.
Yeah.
And what is the new idea in reliable learning? It's some combination from previous 3 points, or what you really want to establish this reliable machine learning?
Right. So along this line, maybe I don't really say a big jump. So based on our previous research, still like by combining some ideas, we should be able to achieve kind of super robustness. So that's our like realistic goal. But of course, we have some more dream challenges over there. But it's not scientific yet.
May I ask a question?
Yeah.
So currently, I think many people train a foundation model and apply to a downstream task by using fine-tuning. So what's the relationship between this and the distribution shift? What you talk about?
Right. So suppose like foundation model is something pre-trained, and that can be used as a kind of knowledge base for our inference. Then, so for example, this scenario can be basically regarded as fine-tuning. So in the training phase, so this is more like pre-training. We have huge amount of label data and we pre-train a big model. Then in the test phase, we only have unlabeled data, small number of unlabeled data, and distribution is changing over time. Then we update our pre-trained model. Actually, in this research, so we basically consider a linear model, online convex optimization. So model is linear and loss function is convex. So it's nothing related to neural network. But in the training phase, we can train a huge foundation model, then fix all the feature extractor. And if we only update the last layer, it's linear prediction. Right? Then the same theory can be actually applied to this sequential distribution shift. So in a sense, this is one method that achieves like fine-tuning in a theoretically guaranteed way. But feature extractors are fixed. So that's the current limitation.
Got it. Thank you very much.
Whether we have a workshop on fine-tuning at NeurIPS this year.
Oh, really?
So it includes this topic as a special case. I don't call it fine-tuning by myself, but I call it online learning.
Yeah. But the problem essentially is same. So downstream tasks have different distribution.
So
right?
maybe depending on the people, I think the definition of the term is a bit different.
Okay.
But roughly they are overlap, fine-tuning and online learning.
Thank you. Okay, if no more questions, let's thank Professor.
So I'm very glad to here to give some work on tensor manifold representation. And the topic will cover, so how to represent data information in this entangled way, and how to train such model, and how to use this model to real application. So the motivation for tensor representation is, now we know that the artificial intelligence is a very hot topic, and the deep learning model is very good for extract visual pattern or even multimodal pattern. And the recent trend is move to large model, basic fundamental model. And what's new problem in these models? First challenge for AI model is that the prediction is unexplainable, and also weak OOD generalization, and especially when we face long tail distribution, and then the prediction probably provides wrong prediction. And also for generation model, there's another new issue come is that hard to control, and still another is that hallucination problem, that it generalizes fake things, that it's a new challenge. And why this happened, and what is the key scientific challenge problem for this problem, is that for deep learning model, for represent data, is that we lack of new semantic representation. And for generate model is that controllable is still new problem. And our idea how to embed it, the common knowledge to help artificial intelligence system to predict more rationally. So first things is that for deep learning model, usually take image as input. Take this example that once we add noise to the input image, and the new model probably make complete wrong decision. This is already found. This problem is already found almost 5 years ago, and why this happened, and how we can reduce this problem. We cannot directly solve this problem, but we try to improve this problem. First thing is that dimension curse problem. Dimension curse problem, once you add noise to an image, so the noise image in the embedded space is quite, the distance between the clean image and the noise image will become very large, although the noise is very, very small. And the second thing that is we project higher dimension data to the lower dimension space. For example, in the embedded vector space, for the image, take, for example, we take 256 size image times 600, 200, this one. And the dimension of original image space is 65,000 dimension space. Once we project to lower dimension, n is, for example, 1,000 dimension space. And this projection actually will cause new problem. And the problem is that in the lower dimension, once your previous clean image, for example, the panda vector is here, and once you add new noise to the panda image, and then this embedded vector will shift complete away from this point. And another problem is that the inverse of this panda vector embedded space, there is a big space from many submanifold. Problem is that the complete this original space dimension with dimension 64,000 space, all this data will project to the same point. And by using softmax classification, of course, all this image will classify as a panda. So this is the higher dimension curse problem that, and still another issue we face is once we use generative model to generate image, and the model actually is that just use conditional prediction, that from sequence to sequence prediction. And the model is completely depends on the data. So once we use image, for example, use language model to generate as a visual image, and it looks good, but actually once you look at detail of this image, you will find a lot of unreasonable things. For example, the hand thing have a complete different unrational structure in the generated image. And how we can try to improve this problem, and we propose that we believe that we need to use visual disentangled representation and try to find different components of the representation. And so by what kind of model we will use is tensor, rank 1 tensor decomposition model. For original embedded vector, we try to decompose them to the discriminate component subspace and the attribute space and also pose space. So by decompose the embedded vector into different content and try to use different content, give disentangled model to control the image generation and try to implement in this model. And the first thing is how we learn this tensor 1 decomposition. And we have a very good job from Qibin and joint work on rank 1 tensor decomposition. And try to use this rank 1 model, tensor decomposition model, to find the dimension or the rank of the data locally. Locally, we use linear model, and then we change the center of the data and then try to find the embedded subspace by using tensor 1. And the second thing is how to connect different local representation. Is we try to apply the information geometry to connect the different local tensor 1 decomposition and to provide lower rank manifold decomposition. So how to learn this model? And then we develop called information bottleneck disentanglement criteria. Previously, we know that there is an information bottleneck criteria. Try to compare the original input data, original input x to the bottleneck t, and minimize this information and try to maximize the embedded t with y. That by using information bottleneck and try to predict the output, this is the theory or the model of information bottleneck model. And we see that some theoretical analysis see that once we provide the constraint of the compression, increase the compression data beta, increase beta, and that will degenerate the performance. And how can we try first give the lowest compression and also try to find the information or precision, also keep the precision. We are trying to use this disentangled representation model. Idea is that here is the input data, and we are trying to decompose X into two parts. One part is information bottleneck part. Another is the rest of the part. Try to decompose of this representation and disentangled and try to use the information bottleneck to predict, and also try to make these two parts as independent as possible. And the second one is that we are trying to maximize the connection between this one. Previously, for information bottleneck is try to minimize this part. But for our representation, this is the dimension reduction, and try to maximize this, but try to decompose these two parts and use information bottleneck to do the prediction. And by using this model, and then we try to learn the corresponding model. Here just give some criteria for learning the model. And what kind of idea, for example, how to make the content of subspace as a lower dimension as possible, because once you make the object dimension as lower dimension as possible. That will make the prediction more robust. And for example, here, if we have a panda submanifold here, and also Jimbo submanifold here, and if we do not make the subspace during the training, make the subspace as a low dimension as possible, probably now a small noise will in the embedded space will classify as Jimbo, and so keep the object dimension as low as possible is one way that can make prediction more robust. So in order to make this, we provide some constraint for a disentangled representation. First things is that we are trying to train a model that, for example, separate from, this is just illustration of the toy model to explain the idea, is that if we are classifying object, this object, and try to separate object with background, and then we can decompose the object with background, and then change the background will not change the front the object. And by using this idea, propose a new structure, alpha structure, to represent the data and train the model, try to change. And there's still another constraint we called beta. Beta structure is using change of the pose information. Try to change, once we change the pose from one pose to another, and then we'll keep the content the same. And so the second structure is called the beta structure. Is using the beta structure is try to keep the pose invariance representation. Okay, here is the implementation of some criteria. I will not go detail for this representation, and just try to decompose or disentangle the pose information from the content information. Here, just give some simple toy model to show that the constraint for training alpha structure and beta structure will keep the content information invariance with change of the background or change the pose information. So still another problem once we use the model to generate model is that model collapsion problem. Model collapsion problem is that once you train a generative model, and then the model generative model mainly from the training data, the pattern from training data. For example, here is the bat diversity that all the bird is trained is in the same pose, and lack of diversity. And if we try to make diversity of image generation, and then we need to make the from representation model and try to make the model diversity as possible. How can make this possible? And actually it's kind of distribution of the representation. And so we are trying to make the uniform distribution in the embedding space, or sometimes we call the noise vector to generate. We are trying to generate, but this noise level is not in the whole space, but in the subspace. But by taking subspace, submanifold noise, and try to make them distribution as uniform as possible, and we'll generate model. The idea is that we are trying to, once we train the model, we are trying to make the representation in subspace, submanifold space as uniform as possible. And what is the uniform in the representation space is try to make the Hansen matrix as a diagonal space as possible. And this is the constraint for the model generation. Here it gives some example that, for example, original training data is distributed as this. So there is no training data in this space. Once you try to generate model in that space, there is a missing distribution. So our model is, although this data is missing, but during the training model, we are trying to make the representation space as uniform as possible. And then using our constraint, and then we will see the generated model will be more uniform. And then there is, can generate diversity will become much more better. Here is just give some example. So we are trying to use the model to do multimodal visual question problems. And once we try to understand a visual information, and for example, VQA problem is ask once you provide the video and ask your questions. For example, here, what animal is jumping into bag at office? And the real background in this video is a kangaroo. But in this environment, once you directly use the model to do the prediction, and then giving indoor space cat probability is much higher than indoor prediction with higher probability than kangaroo. And so once we have very rare case happen, and then how can we make the prediction? We are trying to use the causal intervention model to remove the bias prediction. And the idea is that for example, here is still another things is that one person is running while running and shooting. And generally speaking, running and jump is much higher than running and shoot. So in order to remove this bias or long tail distribution samples, and then we try to use the causal information, use prior knowledge to remove this bias. And here is some work result. And still another approach for VQA is because in VQA, some question is complicated. We cannot directly, by embedding this sequence model into one embedded vector or token to do the prediction. And the first step is try to decompose the question into sub-questions. And each subspace is very simple to check. And then we use some hierarchical decision model to do the prediction and make the prediction as precise as possible. And so here is some demonstration. I'm not go to very detail of the problems, and the idea is try to use knowledge proxy intervention for the confounder VQA problem. Okay, still another easy understand application for the representation is another issue is clothing try-on problem. We know that now online shopping is very, very popular worldwide, but we still cannot easy to see, for example, for a clothing, is it fit you well or not? It's good looking or not? But so the technology for this virtual try-on problem is, once you have tried to buy a clothing, and then you just standing on camera and see the virtual try-on system will automatically put the clothing on to fit your body, and see if the color or the pattern or the shape is fit to you or not. The idea is that we are trying to provide some technology to support these problems. So in order to solve this problem, we need to divide this into two issues. One issue is the pattern of the clothing is different from the pattern of your body pose. And we need to first try to wrapping the clothing into your body. This is the first step. And the second step is, once this just directly wrapping the clothing to your body is not good enough. And we try to use wrapped model as a condition to regenerate the image, regenerate the image like this. And here, first step is found the wrapping model. Wrapping model is trying to find the shape of your body and transfer the clothing to the shape of your body. And then by using generative model, condition generative model, to generate new models. Here just gives some example. So this one is the human body, and we are trying to put the clothing here to the body. And this one, the last column is our model. And we will see that our model looks quite good visually, see, because it's not easy to use some experimental result for solid. And also you can change, for example, clothing, exchange the clothing. For example, if this is you, and also you are trying to take, for example, some famous people, and look, that clothing looks good, and what will the clothing is look like if you try on you, and then we can try to fit this model. Some example, for example, we can develop the idea for this segmentation model for, and also we provide some open code and the data and tools. For example, our image composition toolbox is already adopted by Amazon, their platform for image editing. And okay, that is a conclusion of my. Semantic representation is very, very important, and also causal inference is extremely important during some higher fidelity inference problems, especially for driving car, and how to make the generative model more controllable is my future works. Here is some acknowledgement of our group, our student, and our collaborate. Okay, thank you.
Okay, thank you very much. Any quick questions? So can you mention something about computational complexity of the proposed methods?
Complexity.
Tensors and geometric optimization are kind of heavy in computation.
Yeah, actually, it's a very good question. And we try to make this first step is make the prototype. We cannot really apply this model at this moment to many heavy, for example, the human body generation problems. But for human body generation problem, now we cooperate with another company is try to use the generative model. For example, 3D model for human body, but we just try to estimate the pose. But the generation is implemented by 3D model.
So in that case, you don't have to really handle like huge data directly.
Right. We just want to estimate the feature or the pose or content or texture, the pattern and the classification, and really generated by some 3D or computer graphic problem using that to generate.
Yeah, thank you very much. Any other questions?
Yeah, I have a question about this the entanglement learning, representation learning using rank 1 tensor. So could you explain a little bit more about why the tensor is good for this task?
Right, good. So in the object manifold space, in the embedding space, generally for one type object is located in a subspace, not the whole space. But generally, this manifold is very difficult to find the representation. And tensor 1 decomposition provides two good things. Is one, the number of rank 1 tensor is index of dimension. And the rank 1 tensor, we can also learn this tensor representation locally. And then by using connection of the local tensor and become the submanifold tensor decomposition. So this is because this is computable representation. Yeah.
Okay, thank you.
Okay, let's thank Professor Zhang for the great talk.
Okay, thank you.
Yeah, today I'm going to talk about efficient and robust machine learning with tensor network. Okay, and we know that now the big trend of machine learning and AI is the large model, and the scaling up is a scaling law is very important. So that means we need more and more large data set and train a huge model with a lot of parameters, and also need a lot of training computational resource to train such a big model. And one typical example is shown as here, GPT-3. It costs a lot of data hungry, and the model is huge, and a lot of computation resource, and cost a lot of money. So one question is interesting question is, so if we need more intelligence, can we always need to scaling up, like more data, more big model, or more computation? So some people wonder, maybe this is not a real intelligence. So maybe we need to consider how to make more intelligence or method without always scaling up. So we several challenges. Let's start from data perspective. Actually, in many applications, especially bioinformatics or biomedical, sometimes we don't have a large, high-quality data set to train a good model. Data may be incomplete, data is limited, or data is noisy, and sometimes even data is artificially destroyed, corrupted by adversarial attack. So all of this situation, maybe sometimes we cannot train a huge model to solve such problem, like a recommender system, and the image imprinting if we have only one image, and also a graph predictions. For the model perspective, as I think deep learning already show very successful and many applications, and theoretically already proved that over parameterization doesn't give the overfitting. However, there are still many problems when we have a big model. Like one is interpretability. The model is considered as a black box. We cannot understand how this model works and how each node a neural represent. And when we have a decision, we don't know why this decision get from the input. Also lack of robustness to adversary attack. So when one image, just very few pixels or a little bit perturbations will change to completely the output and will be considered as adversary attack for such model. So we address this model. Our team is basically work on tensor-based machine learning, and that means we formulate many machine learning problem, and we study the fundamental method technique, which is tensor method. We try to find what kind of challenges in machine learning can be solved by our tensor method. So in many methods, like tensor-based method, is based on tensor decomposition, or the fundamental task is how to learn a limited tensor entries, or how to learn a tensor structure from limited data or noise data, and or some incomplete data. And finally, we try to capture the data tensor structure. Then we can do the reconstruction of the whole tensor, complete tensor. We consider this is the ground truth. But to do this task, there are many challenges we should address. One is data efficiency. So like how to develop a better method, just using a few observations to reconstruct the tensor. And the second is efficient algorithm for optimization. And theoretically, we also want to have a theoretically guarantee for such method. So we will address many problems we can consider as efficiency. So not means computational efficiency, but like data efficiency or parameter efficient. And recently, we also use tensor network. So what's tensor network? Tensor network is one extension of tensor method to high order case, because when we give a tensor, 3D tensor, people most know that two popular tensor decomposition is like CP or Tucker. It's just an extension of matrix factorization to 3 order. But when the tensor is a high order, n is much larger than 3, there are so many flexible tensor decomposition case. And in this case, we talk about, we give the name tensor network because there are a lot of factors. They have different connections, different structures. So like tensor train or PEPIs or tree structure. And another research line is in quantum physics. Quantum tensor network is a very important tool in quantum physics to describe the many-body wave function. But in our case, we just consider this is mathematical tools to represent a high-order tensor, like n-order tensor as a contraction of n small tensors. So which is just change the dimension from polynomial n to the linear to n. This is a particular tensor network we call tensor ring decomposition. So let's try to understand the tensor network. So each element in the tensor can be represented as a sequential product of matrix. And each matrix is just extracted from each core tensor core according to each index. And then finally, we have a trace operation to ensure the output is a scalar. And this is a ring structure. So this is just one type of tensor network. There are many different tensor networks. And this is a tensor network or tensor decomposition. They are just a model. So next, task is how to develop a method to decompose data according to the model. And until now, many tensor methods, actually, this is just a general framework. We need to know that like distribution of data. This means likelihood function you need to define. It's a Gaussian distribution. And this is just one assumption we need to predefine before we develop method. And second is structure constraints. That means we need to assume which tensor decomposition we will apply, like a CP structure or Tucker or tensor ring, which we talked about before. And usually these assumptions need to be predefined. But in reality, I think the data maybe not have different distributions, and maybe we don't know which structure is better. So we try to further develop a more flexible and powerful tensor decomposition method. One idea is to use joint distribution. We just model the joint distribution of data and the latent factors. And this joint distribution is proportional to exponential family distribution. And inside this is the energy function. So this energy function, we use a neural network to represent this energy function. Then by using such joint distribution, we can model, I think, any type of more flexible distribution. So next task is how to develop an algorithm to learn this model. So we just use a contrastive learning technique and to define some loss function to learn this model, because we use a neural network to model such distribution. So we can model any distribution, and also the decomposition is extended from linear decomposition to nonlinear decomposition. And when we use a neural network to extract the representations, or when the data has noise or data is incomplete, and actually tensor method can be also used as a regularizer for learn the representation. This is one example. So if we have a time series data, and we can try to create a rank 1 tensor M. And if the data is incomplete or noisy, so we just use a tensor low rank assumption on M, and using this as a regularizer, so we can better to try to find a good representation. And also because sometimes the noise is not always Gaussian distribution, and noise may be outliers and a special distribution. And even the outlier has some kind of tensor structure. So in this work, we tackle about this robust tensor decomposition when the outliers has different structures, like element-wise sparsity, or the fiber-wise sparsity, or slice-wise sparsity. So because in traditional methods, usually only, I think, element-wise sparsity is considered in matrix case. But in tensor case, there are many, more situation we can consider. And some real application is we take EEG data as examples. So when you record EEG data, and sometimes one channel is not connected very well, and this channel maybe is disconnected or corrupted. In such case, we consider this noise is outlier, and in spatial fiber-wise, the sparse outliers. And similarly for some like mode 2 outlier or mode 3 outlier, it depends on how do you organize your data. Okay, next part, I will talk about the parameter efficient modeling using tensor network. So one important task is how to reduce a large model to smaller model. So one task is model compression. So we hope to use like less number of parameters, but have comparable same performance as original neural network. So, but in neural network, usually the weight parameters are always matrix. So how to use like powerful tensor tools to solve this problem? One idea is we first tensorize the matrix W from two order to high order case. Then we assume this satisfies tensor network structure. to use tensor train to represent these parameters. Then the size of parameters will reduce from the m times n to this root mn. But the important is here is the rank r. It's really r squared. So it's really depend on if this has a good structure. If the r is low rank, I think you can get a lot of big compression rate. Otherwise, maybe you cannot compress the model. And if the parameter represented as a tensor train, it's better to also represent like input and output as a tensor network or tensors. Then we can use tensor network operation to do the inference or to derive the gradient. And also tensor operation can be used when we have a multimodal learning, several different representations. And we can use tensor product to do the information fusion. And this example shows that when we use just the tensor product of three model representations, we can get interaction between any pairwise model and also triple interaction of three model representations. Then it shows that if we use such information fusion using tensor product, our performance can be improved. To furthermore, we can also develop like a high order tensor fusion technique. So idea is we first concatenate all representations together, then using tensor product with itself for p times. Then using this operation, we can get more feature interactions, not only linear, bilinear, and trilinear, but also intramodal high order interactions of features. And we can, if we have more information, so in general, we will get more better performance. But one big drawback is our dimension increased exponentially with p if we use a high order tensor product. So in this case, how to solve this? And I think we must use tensor network to represent the parameters as I presented in previous slides. Then the parameters can be reduced again back to the linear to p. And this idea can be applied to RNN. And we consider like input of state H and the input of X as two model representation, and using such idea to change the RNN neural network. At the same time, we just remove the nonlinear activation function sigma because the tensor product is already have nonlinear functions. And we show the advantage is when we use a high order P is large, we can generate the long memory for a recurrent neural network. And when we use small p, we will generate short memory. And this is the big limitation of recurrent neural network. And because when we use tensor network, one practical issue is how to choose which tensor network we need to use. And the rank, how to choose the best rank. Also the order of tensor cores. So all of them are considered as hyperparameters, but it's very difficult to tune all of these hyperparameters. So one is topology, like a range structure, train structure, tree structure. If we test all, and it's time consuming. Also the order of tensor cores and the rank, each rank. So we also develop many methods for tensor networks structure search to handle these issues. So this is our objective function. So we try to basically two terms. One is model expressiveness. That means given your task, if your task is to represent the data, maybe this part is just error information. If your task is classification, you can use the classification loss function here. And the first term is most important. So we want to have a model complexity is much simple as possible. So like which tensor network has less parameters? This is the basic idea. So based on this, we developed in past few years many algorithms. And the basic idea, because this is not a continuous optimization, so basic idea is we use sampling technique. We first sampling some optimal solutions in a fixed area and evaluate the performance, then sample the next one. Finally, we try to find the one optimal solution. And recently, we also consider if large language model can help us to do this kind of research, like they can understand our code or to do reasoning, or even to invent some new type of algorithm. And this work is published in SML this year. And I think tomorrow, Zhao Li will give a talk about these details. And another problem is robustness. Here we talk about adversary robustness. When we use tensor method to represent neural network parameters, we are wondering, one question is how robustness changed by using tensor method or low rank method. So we compare these two neural network. One is a standard neural network with matrix parameters. Another is tensor parameters with tensor operations. And I just give you final conclusion or theoretically results show that in standard training setting, the generalization error bound doesn't related on the number of parameters. But when we use adversarial training setting, in this case, the generalization error related with number of parameters. So that means if without using low rankness, the generalization error bound is large. And when we consider using low rank tensor method, and it shows that the error bound is smaller. So because the low rank representation actually is equal to effective parameters. So here is the effective parameters. And to address robustness, adversarial robustness, I think many people know this example. And most powerful method is adversarial training, to train a neural network from start by using adversarial training. But another technique is adversarial purification. So this technique is try to, like, given an adversarial example, how to develop a new model to try to purify image, to try to remove perturbation. Not necessary to remove all perturbation exactly, but just remove something which may damage our neural network result. So we call this purification. And both these two techniques have advantage and disadvantage. Like adversarial training usually is very robust on the known attack, if you know the attack, and not increase the inference cost. But it's the bad thing is when we generate a new attack, unseen attack, adversarial training usually will fail if they don't consider this general training. And also the need substantial training costs because they need to retrain the neural network. Adversarial purification is, I think, usually better to generalize unseen attack because they doesn't consider a particular attack in training case. However, it will need additional inference cost because we have a new additional model when we have a new test data. So in the following, we have worked on this, and we try to improve current adversarial purification technique. And one of the powerful methods is diffusion model to do this task. However, the diffusion model usually is pre-trained, is huge model, and it automatically can do this task. But we think this is not specially designed for this task. So we further improve it by define a new loss function. We can use adversary loss signal and to guide the diffusion for fine tuning. So that means we just use diffusion model, and we fine tune the diffusion model using using the true label output as loss function. And another idea to improve diffusion model for this task is using guidance, because diffusion model, even fine tuning is time consuming. But actually, if we don't want to change diffusion models, we just use a guidance. So we can define different guidance. So the guidance means when we do backward processing, we just plus a part. This part is some kind of guidance. We don't need to retrain the diffusion model. So it's dependent on your guidance. And our idea is to keep the original, keep the purified image. Doesn't change semantic information. But at the same time, perturbation will be removed. So given this idea, we try to use guidance defined as this. We keep purified image at each of the adjacent step similar. So that means each step will be as similar as possible, and dissimilar from other purified image. So using this guidance, we can avoid big issues like diffusion models. When you input a panda, maybe after purified image, it's become another object, because they will consider remove too much perturbations and even change the semantic information. And finally, I think most adversary technique is considered for supervised learning. So I think now foundation models and the mining technique is based on pre-trained model, usually is unsupervised learning or representation learning. So our idea is maybe, first question is if unsupervised learning is robust or not. And second, I think we should develop more robust unsupervised learning. So here we take one example is multi-view clustering, because this is unsupervised learning and usually is considered as a robust method because of multi-view representation. So we try to first study if this model can be also attacked. And because this is unsupervised learning, so we don't have labels, how to attack is also we need to consider. So now this is a general idea to attack such model. So we consider if we can find a perturbation, which is very small, and put into the image X and change the representation as large as possible to maximize this. But in detail, I think this is just a general idea. We have a more complicated algorithm to attack like a complementary information and also consistent information. And next is how to make robust multi-view learning for clustering. So we similarly, we use adversarial training technique to develop a new method. Due to the time limit, we can skip this part. But in the poster session, you can look, I think we have a poster for this. So finally, in summary, I think tensor network is a useful tool for representation of high-dimensional structure data and also for high-dimensional parameters. So we are now focusing on efficiency of parameterization and also robustness and the interpretability of tensor network and tensor network-based models. So I also would like to thank my team members and the collaborators for their great contribution.
Okay, thank you very much. Questions?
Thank you for your wonderful talk. So you mentioned that it's difficult to determine the hyperparameters of tensor network. So what kind of metrics do you use to evaluate the goodness of the hyperparameters?
Yeah. Actually, we hope the model is simple as possible. So one simple way is evaluate is number of parameters. Like given a data, if we same performance or same representation error, which model use less parameters. That means less dimensions.
Downstream task.
Yeah, we also need to consider, performance, and at the same time, the model, we need compact model.
Very interesting talk. And so you mentioned that use tensor train to simplify or reduce the dimension of the data. So giving a tensor, how you decide the structure of a tensor train, including the length of train and the rank of each matrix in the train.
You talk about the tensorization, right?
Tensor train, tensor train model.
Yeah.
Tensor ring model. Tensor ring model. How to decide the structure of tensor ring or tensor train?
Okay, so you mean how many cores or?
What is the length of the train or each tensor in the subtensors, the dimensions?
Okay, in general, this is just depend on your data. Like your data is a matrix, you can consider it's a tensor ring with 2 cores. If your tensor is 3 order and just 3 cores and as a ring structure. When we talk about the tensorization, means we can change data from the low order to any order. Now, then we need to consider like how long, what is n is best. So in quantum case, like each dimension can be smaller as 2. We can change any data to 2 by 2 by 2. Like if your data is 1024, you can consider is a 10 order tensor, and each dimension is 2. And people call this quantum TT.
Okay, thank you.
I want to ask about computational complexity again. So suppose you have a tensor structure, then like inference is quite fast. Right? It's low rank and it's quite efficient. But if you have like full rank data or whatever data or full parameter matrix, then if you tensorize it, it is computationally quite intensive. Right?
Yeah, if the parameter is full rank, if we
we don't know, so we have some data or some parameter, and we want to approximate it by low rank tensors. This decomposition takes some time. Right?
Yeah. One is you already have pre-trained model, you decompose it. It takes time. Another idea is we train the model from beginning. We just assume this parameters is decomposed as tensor train. So we just learn tensor train latent factors. And we don't do tensor decomposition.
I see.
Yeah.
And how does it affect the latter half of the talk? You have like adversarial robustness and some other kind of application of tensor networks. Is it how does computational complexity changes if you consider a tensor structure? Like for example, adversarial training.
Yeah.
So does it? How does the computational complexity? Is it affected by tensorization, or is it the same as standard case?
Yeah, we haven't considered this issue seriously. Adversarial robustness, this work is about a theoretical study. So we haven't developed algorithm to solve this. We just analyze theoretically. If the parameter, we assume if parameter is low rank, how robustness is changed. Yeah, but this is a very good question. I think in the future we can consider.
Okay, then thank you very much.